Good day. Our topic for today is all about doping. What do you mean by doping? What are these doping elements? What happens to the semiconductor materials after the doping process? 3. Doping is adding impurity to an intrinsic crystals to alter its electrical conductivity. It is also one way of increasing conductivity to a semiconductor. The electrical property of pure semiconductors, such as silicon and germanium, can be greatly modified by introducing a trace of another substance into their pure crystal lattice. The introduction of an impurity to a pure semiconductor is called doping. There are two ways of adding impurities to a pure semiconductor. One is by adding donor atoms, and the other is by adding acceptor atoms. The nature of the doping elements determines whether they are donor atoms or acceptor atoms. P-type semiconductors. Elements such as boron, aluminum, gallium have 3 valence electrons in each the outer shells of their atoms. A silicon crystals doped with large number of trivalent impurity atoms results in many holes or vacancies in the covalent band structure of the material. Si yellow stands for intrinsic semiconductor. B blue stands for p-type semiconductor. 10 cents free electrons, 5 cents holes, 25 cents electrons. Boron has 3 valence electrons, each in the outer shells of their atoms. Each of these atoms has to borrow an electron to form a covalent bond. They are called acceptor atoms or trivalent atoms. A covalent bond needs 2 shared electrons. Since boron has only 3 valence electrons of the semiconductor sharing atoms such as silicon, it will not have partner in the covalent bonding. Therefore, 1 more electron is needed to fill the gap or hole to stabilize a shell structure. When boron is added to silicon as an impurity, the positive hole in its outer shell readily accepts electrons from silicon. Electrons move from one atom to another hole such that an electron moving into a hole must leave a hole in the atom where it comes from. The direction of the movement of the positive hole appears to be the opposite that of the direction of the moving electron. The silicon becomes a p-type or positive type semiconductor. In a p-type semiconductor, the conduction is due to the movement of holes, which can be imagined as positively charged particles. A hole means a lack of electron. The current is said to be due to the movement of the holes, which is in the same direction as the conventional current. Holes are considered to be the majority carriers, and electrons the minority carrier. N-type semiconductors. Element antimony has 5 electrons, each in the outer shell of their atoms. They are called donor atoms or pentavalent atoms. Suppose antimony is added to silicon. Each atom of antimony forms a covalent band with 4 atoms of silicon surrounding it. Though antimony has 5 electrons in its outer shell, only 4 of these are used to form covalent bonds with the semiconductor. The extra electron will be dislodged and free to move around. Since it is loosely bound, very little amount of energy or very low voltage is needed to detach it. Many electrons such as this become available. The conductivity of the semiconductor becomes higher. After the doping process, the semiconductor, silicon in this case, becomes an n-type or negative type semiconductor. Electrons are considered to be the majority carriers, while holes are considered as the minority carriers.